Thanks, Shadash, for the introduction. Yeah, so I'm Akshay. I'm the co-founder and CEO of Marimo, the company. We are most well known for developing the Marimo notebook. Marimo is an open source Python notebook that can be used in 4 different ways, actually, 3 different ways. So it's an interactive notebook, but it's also stored as a Python file, so you can use it as a script or reuse it as a Python module. And you can also share or deploy it as an interactive data app and interactive web app. In this talk, I'm going to give a demo of sort of how Marimo works. It's just best understood by example. And I'll talk about how it works underneath the hood. And the key thing that powers Marimo is by representing Python notebooks as a Dataflow graph. And this intermediate representation powers these 3 different ways of interacting with the notebook. But first, this crowd is usually different. It is different from the crowd that I usually talk to for talks like this. So how many of you guys have heard of Jupyter Notebooks? Okay, cool, nice. How many of you guys have used Jupyter Notebooks? How many of you guys like Jupyter Notebooks? Okay, a lot less, okay, good. Yeah, so I guess, okay, so a bit about me, and you can look at these GIFs for entertainment. So my background is in computer systems, but also in machine learning, and I wear different hats at different times. So I used to work on the Google Brain team as an engineer on TensorFlow, on TensorFlow 2 specifically. So I worked a lot with Dataflow graphs there. After that, I did a PhD at Stanford where I worked on convex optimization, but I also worked on vector embeddings and experimented with algorithms for computing low-dimensional representations of high-dimensional data, such as the graphs or the plots, the GIFs that you see on this page. And so during my PhD, I did in fact do a lot of work in Jupyter Notebooks. Not the library development, but when I needed to apply algorithms to data, I needed to iteratively interact with my data, right? Like you make an algorithm, you apply it to data, you see what happens, that informs the next thing that you do in your algorithm development. And so that way working with data is, like machine learning is different from traditional software engineering. And I quickly became pretty frustrated with sort of a number of things while working with Jupyter Notebooks. Why are we talking about notebooks at all? Notebooks, despite a lot of the complaints that software engineers have about them, because they allow you to visualize your results as you sort of hold your data in your hands, they power breakthroughs in research. They level up communication with literate programming because you can mix markdown, code, and outputs. And maybe relevant for this crowd, like they let data engineers, data scientists, AI engineers, ML engineers work with their data wherever it is, and Databricks, SageMaker, etc. All these guys, the interface to the data for the citizen developer is a notebook. Okay, but I found Jupyter Notebooks, a little bit annoying, a lot annoying during my PhD. What are some of the reasons? So one, I would often make a lot of charts like this. This is an embedding of MNIST if you're familiar with that data set. And the point is these plots were static. I needed to be able to zoom in on a cluster, see what was in that, see the original data points corresponding to them, and I wanted them back in Python automatically for doing more analysis. That was really hard to do in a Jupyter Notebook. In a Jupyter Notebook, you'll get into situations like this all the time, and it's really annoying. This is a Colab notebook. Here I have 2 cells. The first one says x equals 1. The next one prints x, and it says it's 0, so which is it? I mean, the point is that in these traditional notebooks, they're essentially glorified REPLs, just like in the browser, and you can run the cell one at a time. You mutate kernel memory, but there's the runtime has no knowledge that other outputs need to update. So you'll hit a bug like this, or you'll hit bugs like this, where x is not defined on the page. Oops, it actually still exists in memory. And then you come back the next day, the next week, you run your notebook from scratch and nothing works, and you're like, oh my god, what's happening? Oh, this okay, this is actually from one of our users, but I had directions like this too. The file format is not a Python file, right? It's this JSON thing. And there's a good reason for that in some use cases. It's the idea is that they store the visual outputs with the code. But then it's not Python, and so you want to reuse code, okay, I don't want to copy paste, so I'm just going to duplicate the file, and I'm not going to name it either, so you get this kind of sort of mess. Oh, and then if you want to version it with Git, like you run your notebook, you don't change any code, and like, here's my base 64 encoded image, maybe like one thing changed a little bit, or like metadata will change, so it's hard to, version with, just apply regular software principles to it. And then, like these things combined sort of like make like notebooks like really hard to like actually reproduce. And so there's a study from 2019 that like took like 1 million notebooks on GitHub and found that they could only run a quarter of them, and only 4% of those, like when you ran them, got the same outputs that were stored in them. And this is running with the IPython kernel. And you can probably caveat the study, etc. I'm sure there was problems with it, but like I think this like rings true anecdotally for like a lot of people. Someone hands you a notebook, and you're like, oh God, like I don't want to run this, and how am I? Yeah, so they're usually broken. So right, by the end of my PhD, which was I guess 2021, I got to thinking like, what would it take to make a new kind of Python notebook? One where you could have a plot that wasn't static but actually sort of interacted by default. You can make selection, and you got your data back as a data frame automatically. One in which you could actually run your notebook as a script, where you could pull out symbols from the file and reuse functions or classes. One that could, came with like interactive components that would let you make like interactive web apps with no additional effort. Like with these kinds of things, change the way that our community worked with data for the better. So that sort of ideation process led to the creation of Marimo. Like I mentioned, Marimo is totally open source. Apache 2.0, we have a great team working on it, a team of 6 of us. And some of our goals: better developer velocity, so a batteries included experience for working with data, reproducibility and execution and packaging, maintainability as regular software, reusability, module script snaps, and scalability, so affordances for like working with large scale computation. We have a lot of properties. These are listed on our README, which you can find. I hear no marketing, so I'm going to skip the star history slide. I'm going to skip this logo slide. I'm going to skip these testimonials. And I'm going to just jump straight into a demo. So usually I live code, but I have one hand. So it's okay. So this is a Marimo notebook. I have like 3 cells here. The first defines x, the second defines y, which is x plus 1, and the third is the sum of x plus y, defining another variable z.
Akshay, can you see that?
Yes, thank you. Cool. Okay, so the first thing that's going to be different is that if I change the value of x in this first cell, and I run this cell, like watch what happens to the outputs of the next 2. What happens is that they update it automatically. Yay! Arithmetic. Right, but so this is because Marimo is parsing the code in your cells and like figuring out the variable dependencies across them. If I delete a cell, Marimo gives me a name error, so it actually removes the variable from kernel memory and then runs the cells that depended on them, so it invalidates them. So hey, x is not defined, so you don't get that dangling state. If I undo this and bring it back, it repairs the graph essentially. Some of you guys may work with like expensive calculations. You're like, I don't want my notebook to automatically run. In that case, like we have a lazy executor. You just like push this one button or set a config, and then if you change the value of a cell, sorry, didn't keep on this, run it. It just marks the subsequent cells as stale instead of automatically running them, so you still get some guarantees on state, and then you can click this button to bring it back up to date. I mentioned that Marimo, one of my goals is better interactivity. So Marimo is a notebook. It's also a library. You import it as Mo into your notebook, and then you get a library. You get many things, but you get a library of UI elements for one. So if I run this, I get a slider. Sorry, one-handed coding. I replace x with x.value in a subsequent cell. It doesn't matter. But the point is now, all I had to do is say x equals mo.ui.slider, no callbacks, and my UI interactions are automatically triggering reactive execution of dependent cells. And so what's happening here is that Marimo looks and it sees that this variable x is bound to a UI element. And so any interaction here, when I interact with it, it finds all other cells that depend on the variable x, and then marks those for execution, and then transitively runs its descendants as well. One more demo. It's a bit of a toy example. This is a more involved example, closer to the kind of stuff I wanted to do in my PhD. This notebook is arranged in multiple columns just because we can, but also it's kind of nice. I have my logic in the left-hand column, and I have some outputs in the middle. And so in this notebook, what I'm doing is I am creating an embedding of the MNIST dataset, which is a collection of handwritten digits, 0 through 9 images of handwritten digits, embedded into 2 dimensions. And my goal is to find outliers in sort of this clustered space. So what I'm going to do is I'm going to select this cluster of zeros, make a selection, and then it's reactive, meaning that when I make my UI interactions, downstream cells run. And so I've coded this up just using really basic Python to show a preview of the images I've selected, and then this is how tables are rendered in Marimo, and I want to find outliers, so I have the ground truth in this case. I'm going to filter. These are mostly zeros. I'll select everything that's not a zero and kind of see like what that data looks like. Make a selection of my table, and okay, I see some kind of funky looking digits that kind of look like zeros, and I can drill down into this more. The point is that like this was really easy to do in Marimo. Like we can look at the code. So I have some auxiliary code that takes a data frame, creates a scatter chart using a library called altair, and just wraps it in a Marimo utility function, mo.ui.altair chart, outputs the chart, and then the value of the chart is just the selected data frame. And so it's that easy. There's no callbacks. There's nothing complicated. And again, the reason this works is, so as I move this, you can see the data frame above is updating. And the reason this works is that Marimo knows that this UI interaction is bound to a variable called chart, and this cell depends on this variable chart. We have UI affordances as well for that show you the data flow structure. You can toggle a mini map, and I can click through. So for example, this cell that I added that uses chart, I can see that, oh, the chart came from a function that called scatter, and then I can see that the chart flows into other variables such as a table and etc. And so we have a lot of sort of these signifiers or affordances to make it easier to manage your data flow. Okay, one more notebook demo. Well, I guess I can show you the file format real quick. So zoom in. So I mentioned it's pure Python. This is the wrong. One sec. My Tmux shortcut was hard to do with one hand. So this is the file format. So functions that are top level and that are pure and depend only on stuff that are declared in a special setup cell are actually serialized, top level in the file. So like the logic functions I had in the left-hand column, such as this compute embedding function, other utilities are saved in a way that I could just import this notebook as a module and reuse this logic, so no more copy-pasting notebooks and getting untitled 1 through 14. And then otherwise, the cells are just saved as functions, decorated with this little decorator that collects them into the graph. And at the bottom here, there is an if name equals main guard and app.run. So you can imagine if I run this with Python, my notebook.py, it'll do a topological sort of all the cells and then just run them as a script. You can even, everything is just Python. So I had a cell at the end that set up some command line arguments. So I can run this as a script with command line arguments to sort of parameterize the behavior in an arbitrary way. one last notebook demo. In fact, you've already seen it, it's the talk. So the talk that I was showing you is a Marimo notebook. Each output is its own cell. Some of the interactivity that you saw, so for example, the selection I saw of the selectable embedding you saw, that was in fact an embedded Marimo notebook. So you can embed Marimo notebooks in other Marimo notebooks. The way that works is like we embed runtimes into each other, and you can see I'm using the functions that were defined in that MNIST embedding notebook. So you can see from notebooks, import, compute embedding, etc., etc. So you do get composability in this way. Okay. So a bit about the implementation. So we have a runtime guarantee, which is the code on the page matches the outputs you see. So a bit about the properties. So the code on the page matches the outputs you see. Interactive elements, like I mentioned, the way that they work is you bind UI elements to global variables using regular Python syntax to connect them to Marimo's runtime. You can make custom UI elements if you want to with basic JavaScript. Why make a 1D slider if you can make a 2D slider? You can hook up a gamepad and like have those those interactions feed straight into your notebook. So you can really get creative. Okay. Now a bit about the implementation. So from Python to a Dataflow graph. A Marimo notebook is really just a program, a Python program composed of blocks of Python code. So for example, here on the left, what we do is we wire a Dataflow graph on cells based on variable definitions and references. And the runtime lets users use the graph interactively, so as a notebook, or as a script, or as a web app. For reactive execution, which is this property of the code on the page that matches the outputs you see, it's also the sort of the automatic execution is another way that you can think about it. The implementation is sort of in three parts. Dataflow graph construction, static parsing the notebook cells into a directed acyclic graph, and then there's a reactive runtime such that when we run a cell, we collect all other cells that reference its definitions, i.e. its descendants, and also run them. And you also saw that when a cell is deleted or modified, its definitions are removed from kernel memory and its descendants are rerun. So it's another way we eliminate hidden state. So for the Dataflow graph, each cell is a node. An edge from one cell to another means that the second cell refers to a variable defined by the first cell. The important part here is that definitions and references are totally statically inferred, so there's like no runtime tracing at all, which also means that like mutations are not tracked, and that's a trade-off, right? So why don't we trace user code, and what exactly is this trade-off? So static construction, so meaning that the Dataflow really only depends on definitions and references. Well, it makes it really easy for developers to understand what the Dataflow structure of their code is. It's just variables. It's easy for us to implement with 100% correctness. There's no runtime overhead. So it's like a correct representation of the user's code, but it's incomplete because like if you mutate a list, we're not gonna bother to like track that. So like if you start mutating variables in Marimo, those mutations will not be like we won't output. If you mutate a list, we won't rerun cells that depend on that list. And that's just like part of our contract. So if we did try to catch those dependencies, we could catch some of them, but we can never catch all of them, and then you leave the developer in this uncanny valley where the developer can't really predict when they run a cell what else is gonna run, and leads to sort of steep usability cliffs. There are some constraints on the kind of code that a user can enter into a Marimo notebook. The main thing is that the Dataflow graph has to be a DAG. And so that means you can't have cycles, and it also means you can't redefine variables across multiple cells. And that's the biggest thing that our users, you have to get used to it in order to use a Marimo notebook. But if you accept it, if you accept that those simple to understand constraints, you get notebooks that are reproducible, maintainable, and reusable as scripts and apps. You get a lot of benefits. And so we find that a lot of all of our users are sort of willing to sort of make that leap. But it is a leap that you do have to make. The implementation, so parsing is just code in each cell, goes to the abstract syntax tree, and then we do some semantic analysis. So from the AST, you get the definitions, references, and deletes. Then you do some variable scope resolution. So this is an abstract syntax tree. I'm sure you guys have all seen this. B equals A plus 1. There's an assign statement, a binary operation, and then there's some leaf nodes. What's nice is that Python has an AST module, so this is really easy for us to do. We just call ast.parse. You get a parse tree, and it's fast. The AST module, I think, is implemented in C. So honestly, Marimo is a pure Python project. Fun fact, someone once entered our Discord and left when they realized that we were not implemented in Rust. Yeah, true story. But, yeah. So yeah, and it's fast, it's great. The overhead is very small. Semantic analysis, I mean, so once you do the AST parsing, it's basically just like figuring out, if you have an AST for each tree, then now you just need to figure out how the variables flow across from one cell to another. The point is here in this example, there's a global variable called B, that's if defined in one cell, referenced in the second cell. And the third cell has a local variable B, right? It's in the scope of the function, so you just have to realize like, oh, okay, that was in an inner scope, this is not related to the outer variable B, and that's basically it. It's pretty simple. And you can write out an algorithm for resolving these scopes, but it is pretty straightforward, so I won't describe it. And so once you have that, once you have the graph, then you can get reactive execution. So when a cell is run, all other cells that reference its definitions are also run. You can implement state pruning, so that's the thing where I showed you that when a cell is deleted, we know what other cells to invalidate. And that is the sort of basics of our implementation. And a bit about how Marimo uses its graph. I don't know how much time I have. Okay, yeah, I can go through this quickly. So the cool thing is when you have this graph, you can do like a lot of things. But first, like, okay, how do you actually make reactive execution like an experience that people want to actually use in a notebook? Because it is very different from traditional sort of imperative style execute one at a time. So we have some like affordances. I showed you guys the lazy executor. So that's when a cell is run, we just mark to send it to stale instead of automatically running it. We do other like things where like if we detect a cell only has like import statements, we treat those cells specially because people will typically like add a bunch of imports to one cell and go back and add another import. So if we see that, then like we like parse basically the statements. Like we like kind of break up the cell into like multiple conceptual cells and basically special case those to avoid unnecessary reruns. We have like at runtime some control flow functions to like conditionally stop execution, like if a certain condition is not met. And I mentioned we have some constraints, such as like you can't redefine the same variable twice. So you want to kind of enforce those constraints gracefully in a way that doesn't just like piss off the user. So like one principle we have is like no action at a distance. So like if you register a new cell, like if you have these 3 cells, run them one at a time. When you run that third cell, you'll get a nice error in Marimo saying, oh, multiple definition error, but it's not going to go and invalidate the cells the previous cell that had already defined X. So you can formalize that in that sentence that I have here, but that's sort of the basic principle. Memory management, so this was something I actually got asked recently, so I added support for. So like, it turns out I think in like Jupyter notebooks, people will often just reuse the same variable as a way of implicitly like doing memory management, like so they'll have, data equals my large data set, and then later data equals my large data set, and that's so that Python GC can come around and like free up whatever was allocated for that first data set. You can't do that in Marimo, but what you can do is you can use the del operator. So this is a little subtle, but like, so if you have 3 cells, one that defines a tensor, maybe some GPU, one that references the tensor, and the third one that deletes it, but you definitely don't want the delete to run before the other cells that depend on X. So what we do is if a cell deletes a variable, we make it a child of all other cells that reference that variable, so it's automatically like terminal. And then you get some nice sort of things that fall out from that. So like if two cells delete the same variable, they actually form a cycle, and then we block that, so at parse time. So I think it's a decent solution for this problem. Local variables. So this is like people, complain that like, oh, I can't redefine variables. What about my loop variables, etc. So we make the convention that underscored variables are private into like a rule. So if you underscore a variable, prefix a variable with an underscore, we like do some name mangling in the DAG construction and make it local to the cell. And that lets you like get like anonymous scopes by like defining a function whose name is an underscore, and now you have like a local scope for that cell. Composition, so you can import notebooks into other notebooks. When you do that, and you output an entire notebook, we take the original notebook's outputs, concatenate them, show them, including their UI elements, and you can actually interact with the UI elements and it'll like flow through the graph. The way this works is that we have a stack of graphs actually in each notebook. So if you embed a notebook, there's a nested graph, each with its own runtime. The interactions from the front end are like routed through this sort of stack of graphs intelligently. We can convert Jupyter notebooks to Marima notebooks by extending our AST visitor to transform multiple definitions with static single assignment. We have caching, which could be the subject of a whole other talk. Nix inspired. The idea is like if you were to use functools.cache, it would be invalidated on each cell rerun, which is not really nice in a notebook. So we have some of our own cache utilities that are analogous but keyed on ancestor source, primitive reference values, and can also handle closed over values. And the only reason that any of this works is because we have a Dataflow graph and we can reason about whether or not a function invocation is still valid, even if other things have changed. We actually have support for SQL. This is a little weird, but we also parse a Dataflow graph on SQL analogous to Python by specializing on a specific Python AST call nodes. And Python and SQL graphs can be joined based on the return value. So SQL cells return a data frame, Python variable, but they can also reference other Python variables. I already showed you reuse a script. The main idea of this, the way the graph comes into play there is that even though cells are stored in presentation order, we do a topological sort before running them. And then you can reuse as a web app. Honestly, it just comes entirely for free. If you say Marima run my notebook from the command line, it starts a web server, shows just the notebook outputs with the UI elements, and then as you interact with the UI elements, it triggers reactive execution. So wrapping up some of our values, we embrace Python, we embrace constraints instead of trying to plow through them. And the main thing is that we have an easy to understand contract between our programming environment and our users. It has a short description length, which is don't redefine variables, no cycles, Dataflow depends on variable definitions and references. And we have a clear articulation of the value that these things provide and their trade-offs. By having this easy to understand contract, we find that it motivates, it helps users adopt our tool, even though it is very different from a traditional notebook. What's next for us? We have a lot of work in the open source, including a native VS Code extension, the idea of like Marima pipelines, better AI assistance, because you have to. And then also, as a company, we are building a data platform, so we're applying the same design goals of our open source to a next-gen data platform. I can talk a lot about this. Come find me if you're interested. It's not on the slide, but at the very bottom, we are hiring for this, so if you are interested, come find me. In summary, Marima is a new kind of a Python notebook that can be used in 3 ways: as a reactive notebook, as a Python script, as an entire interactive web app. It's built entirely from scratch, no dependencies on IPython or Jupyter. Free and open source. Find us on GitHub, and you can pip install Marimo. Thank you.